Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi. So today we are going to discuss about the module that is Nano-Oxide Structural Ceramics, and it is from the paper Ceramics. So after completing this module, you all shall be able to understand the silicon carbide, silicon nitride, silicons and MAC ceramics. So students, before moving to ceramics like silicon carbide, nitrides and silicons, let us discuss about them briefly first. So silicon carbide, silicon nitride and silicons have been under development and production and use for a long time. The uses include balls, rollers, raceway blanks, mechanical seals and valves, wear plates, sandblast nozzles and even acid pump seals. Some of the other applications where they have been used are extrusion dies, guides and pulleys. Then they have been used in liners, grinding media and components for the pulp and paper making industry. They are also being used in nozzles and reticulate ceramics for molten metal filters, oil field components, tool bits, liquid metal filters, pre-combustion chambers and so on. So such ceramics have very high properties including high strength, high modulus, high temperature capability and chemical inertness, but because of low fracture toughness, no large scale use in demanding structural applications are there. So lately, some new types of nano-oxide structural ceramics have been developed, and in this module we will be discussing about these non-oxide structural ceramics, which are silicon carbide, silicon nitride, silicons and newly developed MAC ceramics. Silicon carbide. Silicon carbide for applications in refractories we have already discussed in previous modules. So as mentioned there, the two major polymorphs of silicon carbide are alpha silicon carbide, which has a hexagonal structure like woodsite, and beta silicon carbide, which has a zinc blende structure like diamond. Of the two, the alpha phase is marginally more stable than beta polymorph. Because of its low thermal coefficient of expansion and high thermal conductivity, it has a very high thermal shock resistance. It retains high strength at high temperatures and has high fracture toughness. It is inert to attack from most chemicals and slags. It oxidizes slowly in an oxidizing atmosphere but can still be used in air up to quite high temperatures, that is up to 17-20 degrees Celsius under certain conditions, and almost up to its dissociation temperature, that is 2400 to 2700 degrees Celsius in the inert atmospheres. So students, you can see the representative properties of silicon carbide, and you can see that the density of silicon carbide is 3.2 gram per centimeter cube. The Young's modulus is 370 gigapascal. The fracture toughness is 3.5 mega Newton meter to power minus 3 by 2, whereas the fracture strength is 390 megapascal. Silicon carbide preparation. So for application in structural engineering products, silicon carbide bodies are fabricated through two routes. So the first is reaction bonding and the second one is sintering of ultra-fine powder with some dopants. In reaction bonding or reaction sintering, a mixture of silicon carbide and carbon are compacted and infiltrated with liquid silicon. Firing is carried out at 1400 degrees Celsius. Silicon and carbon react to form beta silicon carbide, which bonds the pre-existing silicon carbide grains. It is difficult to react the silicon totally. About 8 to 10% silicon remains unreacted, because of which the product cannot be used above 1350 degrees Celsius. In the sintering of ultrafine powder of silicon carbide, the additives like carbon and boron or carbon and aluminium are used. Dopants like iron, lithium and magnesium are also used. The dopants are so selected that they do not decompose silicon carbide during sintering. The carbon plays an important role during the sintering of silicon carbide. It increases the concentration of point defects, which increases the diffusion. It also removes the oxide film at the grain boundary, which retards the transport of vacancies across the grain boundary. The compact is sintered in an inert atmosphere between 2000 to 2100 degrees Celsius, and a complex set of reaction takes place during sintering. Now here comes silicon nitride and its preparation. The basic building block of the structure of silicon nitride is SiN4 tetrahedron. The tetrahedra are linked at the corners. The silicon nitride bonds are short and they are very strong. The silicon nitride powder is prepared by the following process, which we will discuss one by one. So the first is direct nitridation of silicon. This is the method most used in commercial practice, and the following reaction occurs like 3Si plus 2N2 gives Si3N4. Here delta H is minus 175 kilocalories per mole at 1600 Kelvin, so it is exothermic. The melting point of silicon is 1414 degrees Celsius, and the silicon is very volatile at temperatures near the melting point. Also, it tends to oxidize readily, and on the other hand, complete nitridation is not possible unless the silicon is melted. The nitridation is therefore carried out in pure nitrogen atmosphere. So to reduce the silicon volatilization, the reaction is carried out in two stages. That is, for 25 to 50 hours at 1325 to 1350 degrees Celsius, followed by 10 to 25 hours at 1425 to 1450 degrees Celsius. The product consists of alpha and beta silicon nitride phases in the ratio of 3:1 if the temperature is kept below 1410 degrees Celsius, whereas the beta phase increases if the temperatures are used. The other three processes and the corresponding reactions are as follows. So the next one is carbothermal reduction of silica followed by nitridation. In this case, the reaction is 3SiO2 plus 6C plus 2N2 gives Si3N4 plus 6CO. So here delta H is 303 kilocalories per mole, which is endothermic. The next is silicon imide decomposition. So in this, the reaction is SiCl4 plus 6NH2 gives SiNH whole twice plus 4 times NH4Cl at room temperature, and then 3 SiNH whole twice gives Si3NH4 plus 2NH3 at 1200 to 1500 degrees Celsius. The next phase is gas phase synthesis. In this, 3SiCl4 plus 16NH3 gives Si3N4 plus 12NH4Cl. To prepare sintered silicon nitride bodies, several methods are used depending on the applications. So let us discuss these methods one by one. So the first is reaction bonding or reaction sintering. In this process, the silicon powder is compacted into a desired shape. It is heated to 1200 degrees Celsius in an atmosphere of nitrogen or mixture of nitrogen and hydrogen, or it can be nitrogen and argon. So the nitrogen reacts with silicon to form silicon nitride. So initially, alpha silicon nitride fibers grow into the pores of the compact. Then the temperature is gradually raised to 1400 degrees Celsius, and now mostly beta silicon nitride, that is beta Si3N4, forms. So the density of about 85% is achieved, and the final microstructures consist of grains of alpha and beta phases. So the hot pressed silicon nitride is the next procedure, that is HPSN. So in this technique, the silicon nitride powder is mixed with some additives and hot pressed at 1700 to 2000 degrees Celsius. So the hot pressing produces simple shapes. Very high densities and strengths can be achieved using this technique, but for complicated shapes, the hot isostatic pressing is usually used. Now the next is liquid phase sintered silicon nitride, that is LPSSN. So the large amount of suitable additives and the silicon nitride powder is used to carry out the liquid phase sintering. So an inexpensive process is liquid phase sintered silicon nitride, which yields adequate properties suitable for many applications. So a large number of sintering aids are used to sinter the silicon nitride, and some of these are yttrium oxide, that is Y2O3, or magnesium oxide, that is MgO. Now the next is gas pressure sintered silicon nitride, that is GPSSN. So in this process, the silicon nitride powder with sintering aids is sintered at a high pressure, but a high nitrogen pressure is used. So in this technique, a gas is used, that's why the name is gas pressure assisted sintering technique. So the representative properties of silicon nitrides are tabulated in this table, where the density of silicon nitride is 3.2 gram per centimeter cube, Young's modulus is 300 gigapascal, fracture toughness is 7 Mnm minus 3 by 2, fracture strength is 900 to 1200 megapascal, Weibull modulus is 15 meters. Sialons. Sialons are the solid solutions of silicon nitride, that is Si3N4, in which part of silicon is replaced by aluminium and simultaneously part of nitrogen is replaced by oxygen to maintain the charge neutrality. That is, in silicon nitride, Si is Si plus aluminium and nitrogen is nitrogen plus oxygen. So they can be looked upon as a part of the quaternary system, that is SiO2, Si3N4, Aln, Al2O3. So there are three types of sialones with isostructural with alpha Si3N4, beta Si3N4 and silicon oxynitride. So the most common are beta sialones which have the general formula Si6-Z AlZ-OZ-N8-Z. So beta sialones are the most commonly used and they have the general formula which we have discussed in the previous slide is Si6-Z AlZ-OZ-N8-Z. So the sintering aids such as the yttrium oxide, that is Y2O3, or magnesium oxide, that is MgO, or a rare earth oxides are used to densify. More liquid is formed at lower temperatures than in the case of silicon nitride and the densification is better. On sintering above 1700 degrees Celsius, the elongated hexagonal beta sialones grain grow in an oxynitride liquid phase made up of additives such as yttria, alumina, silica and aluminium nitride. The liquid phase forms a high temperature glass on cooling. So the beta sialones have excellent toughness but their hardness, which is 14 to 16 gigapascal, is low. The alpha sialones have higher hardness of 22 gigapascal and this comes from their longer stacking sequence, that is ABCD, as compared to AB for the beta variety. So such a structure provides a high resistance to dislocation motion. Alpha sialones. The alpha sialone materials produced earlier had a microstructure of fine equi-aged grains. Consequently, the material had a low toughness. Over the years, progress has been made to produce a microstructure with interlocking and elongated grains. This has resulted in alpha sialones material of high fracture toughness. In alpha sialone, it is essentially a solid solution of alpha Si3N4 in which there is a standard substitution of the silicon nitride bond with the aluminium oxide bond. In addition, there is substitution of silicon by aluminium and simultaneously filling of the interstitial sites by a cation M. It has a general formula, that is M by Z, Si 12 minus M plus N, Al M plus N, O N 16 minus N, where M is the interstitial cation with a valence of Z. The alpha phase is stable only in a limited composition range. A full phase diagram for alpha sialone has to be quaternary phase diagram involving three cations, that is silicon, aluminium and M, and two anions, that is nitrogen and oxygen. However, a binary phase diagram may be used to illustrate the range of stability with the concentration of M. Such binary diagram is between silicon nitride, that is Si3N4, for which M is 0, N is 0, and M2 by Z, O is to 3 aluminium nitride, where M is equal to 2N, which is shown in the figure in the next slide. So students, you can see a figure on the top left corner of the slide showing the pseudo-binary phase diagram between beta silicon nitride, that is beta Si3N4, and M2 by ZO is to 3 aluminium nitride, showing the region of stability of the alpha sialone phase. So in the figure, you can see that the horizontal composition line in this diagram correspond to M is equal to 2N. In this phase diagram, the alpha Clone exists as a eutectoid phase and its lower solubility limit is nearly temperature independent as shown by nearly a vertical line, while the upper solubility limit increases with temperature. The range of solubility decreases with increase in the size of the interstitial cation. The size of the interstitial cation also has an effect on the eutectoid temperature, where it decreases as the size of the interstitial cations decreases. It becomes so low for small cations that the kinetics of the decomposition of the alpha phase become very slow and the alpha Clone phase is stable down to room temperature. This material is suitable for the practical applications. The region of stability of the alpha Clone expands with decreasing size of interstitial cation M. Thus, when the interstitial cation M is equal to Nd, the stability region of alpha Clone is very small. In this case, the alpha Clone decomposes when held in a particular temperature range. So the particular temperature range will be 1400 to 1500 degrees Celsius. The stability region is quite large for yttrium and Yb, and so these alpha Clones are stable in the useful temperature range. Initially, the alpha Clone ceramics were fabricated using powders having more than 90% of alpha silicon nitride, that is Si3N4, and these particles provided the nucleation sites for alpha Clones grains. This produced an equi-egg structure of alpha Clone, and this material had a high strength but low fracture toughness. So the key to produce alpha Clone ceramics with elongated grains, that is to improve the fracture toughness, is to have very few nuclei for the formation of alpha Clones in the starting powder, and during the heating and forming steps this procedure is taken care. So it has been found that alpha Clone can be produced by starting from beta silicon nitride, that is beta Si3N4, and rare earths in the starting powders. Thus, in most compositions for which the stability of alpha Clone phase is low, the proportion for the formation of elongated grains is more, that is, in the compositions containing Nd. So this is because as the phase stability is low, so the driving force for the nucleation is high, and so very few nuclei forms. So in the case of composition denoted by YB1212, that is M is 1.2 and N is 1.2, which has a very high driving force and a low nucleation rate, a two-step process are used for the formation of glass ceramic. So the firstly, the piece is held at lower temperatures around 1550 degrees Celsius, where the nucleation rate is very low, so that only a few nuclei are formed. Then the piece is heated to 1950 degrees Celsius to form elongated grains from these nuclei. Students, you can see on the left hand side a figure showing the amount of seeds versus fracture toughness for alpha Clone. So even though it is possible to prepare alpha Clone from suitable composition using controlled heat treatment, the dependence of composition temperature and phase stability on the nucleation rate makes the process difficult to control. An easier alternative is to use seeds of alpha-sialons in the starting powders. Thus, the alpha-sialon is first prepared separately and then small amounts of the seeds of this are used along with the starting powder. When the amount of seeds is small, the elongated grains of alpha-sialon are obtained. The amount of the elongated grains and thus the fracture toughness of the material depends on the amount of seed and can be controlled. So students, you can see a plot of the amount seed versus the fracture toughness, and a maximum fracture toughness of about 11 meganewton per meter to power 3/2 can be achieved in Y containing alpha-sialon by optimizing the amount of seeds. However, the fracture toughness of the sialons is still far below for metals and is inadequate for many structural applications. This is also the case for the other ceramics discussed earlier, that is Al2O3, zirconium oxide, silicon carbide and silicon nitride. Here comes Max Ceramics. In 1960s, Hans Notny et al. Discovered that more than 100 new carbides and nitrides, including titanium silicon carbide and titanium germanium carbide, no further interest was shown in these materials until 1990s. When the Bassam and El Braghi prepared large samples of titanium silicon carbide and showed that it had unique properties which combined the properties of metals and ceramic. Thus, it had a high electrical and thermal conductivity like metals and was oxidation resistance and thermal shock resistance like ceramics. Later, they discovered that the titanium aluminium nitride, that is Ti4Al-N3, and it became clear that these materials belong to a family which can be represented by the formula Mn+1 AXN or max phases, where N is equal to 1, 2 or 3 and M is the transition element, A is a group element and X is carbide or nitride. The phases corresponding to N is equal to 1, 2 and 3 are represented by 211, 312 and 413. The transition element, that is M, can be from group 3, group 4 or group 6. No max phases are known with the transition elements Y or Nu from group 3 or W from group 6. The max ceramics have a layered structure. They have a hexagonal unit cell and there are 2 formula units per unit cell. The unit cell consists of M6X octahedra with layers of A element between them. In 211 phase, 2 M6X layers separated by each other by A layer. Similarly, in 312 and 413 phases, the number of M layers separating the A layer is 3 and 4 respectively. In addition to the pure max phases, the solid solutions between them also exist. The number of these solid solutions is quite large and the bonds in the max phases are the combination of metallic, covalent and ionic bond. The MX is strongly covalent like that in the MX binaries, whereas the MD-MD bonding is metallic. Also, the Ma bonds are relatively weaker than the MX bonds. The solid solutions between max phases also exist. The number of these solid solutions is quite large. The max phases have excellent electrical conductivity with resistivity in the range 0.2 to 0.7 microohm meter at room temperature. So many of the MAX phases are so-called compensated conductors in which both electron and holes are the charge carriers. They are also good thermal conductors and their thermal coefficient of expansion are relatively low in the range of 5 to 10 micro per Kelvin. Several of them have very low thermoelectric or Seebeck coefficients. The MAX phases oxidize in air, but some of them form an oxide which forms a protective oxide layer, making them resistant to oxidation. For example, T2AlC, which forms a protective layer of Al2O3 layer on oxidation. This layer also has a good spelling resistance, making this material quite resistant to oxidation. The MAX ceramics have near isotropic elastic properties. They have high room temperature moduli, that is, Young's and shear moduli are 178 to 362 and 80 to 142 gigapascal respectively. They also have a very low density of the order of 4 to 5 gram per centimeter cube. Unlike the corresponding binary compounds, the MAX phases can be very damage tolerant, and therefore while titanium carbide is brittle, damage tolerant and non-machinable, whereas titanium silicon carbide is machinable and damage tolerant. The reason for this is the presence of a high density of mobile dislocation in the MAX phases. The dislocation are Bessel plane dislocations, and however, since the slip is confined only to the Bessel plane and the number of slips system is less than 5, the number needed for good ductility. The result is that the MAX ceramics are ductile under constrained deformation or at high temperature but at brittle at room temperature. Therefore, the deformations occur by shear, band formation or king formation and by delaminations. The MAX ceramics are relatively soft materials. Their room temperature fracture roughness ranges from 5 to 20 meganewton m to power minus 3 by 2. They show an R-curve behavior, the relatively high value of fracture toughness, and the R-curve behavior is due to the formation of plastically deformable bridging ligaments and the king boundaries which arrest the cracks. The MAX ceramics undergo a brittle to plastic transitions, that is BPT, at a temperature above which they are quite ductile even in tension. The BPT temperature of any of the MAX ceramic is found to lie between 1000 to 1100 degrees Celsius. They have exceptional resistance to thermal shock and they do not shatter or quenching from high temperatures. Easily, they are machinable by conventional high-speed tools, and the powders of titanium silicon carbide and titanium aluminum carbide are available commercially for about $500 per kg, which make them quite expensive. They can be sintered in pressureless manner to high density, and despite of its high cost, the ability to do pressureless sintering and to be able to machine to close tolerance may make these materials find more and more applications as the cost of powders drop as the demand increases. So students, let us summarize what we have learned in this module. So far we have learned that the room temperature fracture roughness is around 5 to 20 meganewton m to power minus 3 by 2, which can be seen from R-curve behavior. It undergoes a brittle to plastic transition, that is BPT, at BPT temperature. and it is quite ductile in tension above BPT temperature and can be formed by various methods as much as 25. So BPT temperature usually varies in the range of 1000 to 1100 degrees Celsius. They have an exceptional resistance to thermal shock and do not shatter on quenching from high temperatures. Moreover, they are easily machinable by conventional high-speed tools and primarily because of their laminated structures. So powders of titanium silicon carbide, that is Ti3SiC, and Ti2AlC are available commercially for about $500 per kg, which makes them quite expensive. But they can be sintered in a pressureless manner to high density. Despite the high cost of powders, the ability to do the pressureless sintering and to be able to machine to close the tolerance may make these materials find more and more applications as the cost of powders drop as the demand increases. Thank you.